रिकॉर्डिंग भूल गया था, चालू किया है. लेट्स सी. Okay. So for parallel reactions, there are two types of analysis. One is reactor size and second is product distribution. Reactor size का हमने already unit 3 में किया है, so we will not do it here. Unit 4 is mainly focused on product distribution. That means if there are two reactions, parallel reactions, one reaction gives desired product, the second reaction gives undesired product. So how do we maximize the desired product and minimize the undesired product? So these two analysis, that is reactor design or reactor size and product distribution, actually run counter to each other. That means अगर size minimize करने जाएंगे, product distribution may not be good. If you optimize the product distribution, then the size may not be minimum. So it's actually a economic analysis, and we have to see what is the cost of purification if you get two products. One is the cost of purification goes up because side product has to be separated. Second thing is what is the loss in value because we didn't get the desired product. Okay, so but in general, whenever there is a question of size versus distribution, distribution is favored always because it has a lot of what do you call implicit benefits also, like it reduces our separation cost also. Okay, and in all these cases we are going to look at epsilon A equal to 0 because it's easy to understand with epsilon A equal to 0. That means constant density systems or liquid systems. So first we look at qualitative discussion, qualitatively understanding what is product distribution, how it is affected. So if you have two reactions, A goes to R, which is desired reaction, and second one is A goes to S, which is undesired reaction. So you can write rate of formation of R, RR is equal to dCr by dt is equal to K1 into Ca raised to power of A1, where A1 is the order of reaction with respect to A for R. Similarly, you can write for RS, undesired product, RS is equal to dCs by dt is equal to K2 Ca raised to power A2, where A2 is the order of reaction. Now, if you divide equation 1 by equation 2, you get RR upon RS is equal to dCr by dCs, and that is equal to K1 upon K2 into Ca to the power of A1 minus A2. So when we want to maximize, that means we want to maximize RR upon RS, right? So in that case, Ca or concentration of the reactant is the only factor which will be controlling, and it depends on the order of reaction with respect to first reaction or second reaction. Okay. Now in this case, we are assuming that temperature is constant, so K1, K2 are fixed, and A1, A2 we know it's always fixed. Okay, so there may be situations where we need to keep Ca low or Ca high depending on A value of A1 and A2. We'll see that. First we'll see how to keep Ca low and Ca high, and then we'll see when to keep Ca low and when to keep Ca high. If you have any question, please stop me in the middle because I'm going to go fast because we already done this. Okay, so we can keep Ca low in the reactor by using mixed flow reactor. Mixed flow reactor always concentration of reactant is low because if it is a mixed flow reactor, if the feed concentration is Ca0, the concentration in the reactor is always Ca, which is final concentration. So it is always low compared to PFR. Another thing is if you are using a PFR or batch reactor, then you should have high conversion. So if the conversion is high, naturally the value of Ca or concentration of A will be low. Third option is increase inerts in the feed. We have seen this in thermo, right? Inerts डाला तो essentially concentration, if it is vapor phase, यहाँ पर यही रहेगा because we have considered Ca epsilon equal to 0, but अगर epsilon equal to 0 नहीं रहा और गैस फेज रिएक्शन रहा तो इनर्ट्स डालने से क्या हो जाएगा कि mole fraction of A in the vapor phase will be reduced, and that will lead to lower Ca. Or other option is decrease pressure in the gas phase. Right? These are for epsilon A not equal to 0. right? So if you reduce the overall operating or reaction pressure, that means capital, sorry, total pressure. So this is nothing but YA into P total. Right. So if I reduce the pressure, total pressure reduces. That means CA will reduce. These are four ways of in which, in different situations, and depending on what is the reaction, what phase the reaction is in, we can reduce the value of CA or concentration. And if you want to keep the value of CA high, then we either use batch or PFR, because already always the concentration is higher in a plug flow reactor compared to mixed flow reactor, and same is for batch reactor. Or if you are using mixed flow reactor, then you should use low conversion. Conversion low रहेगा तो already CA high रहेगा. And उल्टा रहेगा इसका, C, remove inerts from feed or don't add feed inerts, तो ऑटोमेटिकली आ जाएगा YA बढ़ेगा तो CA बढ़ेगा. और इंक्रीज प्रेशर इन द गैस फेज रिएक्शन, यहाँ पर जैसे हमने रिड्यूस किया था यहाँ पर इंक्रीज करने का. सो इफ यू अंडरस्टैंड, लो कैसे रखना, उल्टा उसका उल्टा ही रहेगा हाई कैसे रखना. So do you understand this, how to keep value of CA concentration low and high? Okay. There are no questions. Let's proceed. When to keep concentration low and when to keep high. So if you look at this equation 3, now it depends on values of A1 and A2, the order of reaction for the first reaction and second reaction. So if A1 is greater than A2, that means A1 minus A2 is positive. So we will have RR upon RS equal to K1 over K2 into CA to the power of some positive number. Okay. So in this case, if I want to maximize R, I should keep highest value of CA. Right? High CA is desirable, so it increases R by S ratio. So in that case, we should use batch or PFR, which provides high concentration of A and hence favors formation of R. Right? So it will require minimum size. बाकी सब केसेस में ये टू सी, अगर ये दोनों ऑप्शन हो गया, अगर हाई रखने का है तो बैच PFR यूज़ करने का, या MFR यूज़ करना है तो लो कन्वर्शन यूज़ करने का, या इनर्ट्स में ऐड करने का, या प्रेशर यूज़ करने का. These are 4 options for increasing CA if A1 is greater than A2. And other option, other cases when A1 is less than A2, that means A1 minus A2 is negative. So we'll have RR upon RS equal to K1 upon K2 CA to the power of minus some number depending on the order. So in this case, CA should be as low as possible to get maximum R. Right? So low CA is desirable to favor formation of R. And in this case, what do you do? You can use MFR, but this will require large volume, right? So option, either use MFR, or if you are using PFR and batch, use high conversion, और इनर्ट्स ऐड करने का या इंक्रीज डिक्रीज प्रेशर करने का. दीज आर 4 ऑप्शंस. यहाँ पर सिर्फ यही बताया मैंने PFR MFR का, बट अदर ऑप्शंस आर आल्सो देयर इफ केस रिक्वायर्ड. So is it understood when to keep CA low and when to keep CA high? Okay, there are no questions. Then third case is when A1 is equal to A2, that means A1 minus A2 is equal to 0. In this case, the concentration of the reactant doesn't really affect the product. It is K1 and K2 values which will affect the product. So that we have to see separately what क्या effect होगा, because temperature से हम manipulate कर सकते हैं. That we'll see. The product ratio is fixed by K1 by K2 and has not affected by type of reactor, but temperature effect होगा. Because temperature will have different effect on K1 and K2 depending on which factor?
एक्टिवेशन एनर्जी.
एक्टिवेशन एनर्जी. So एक्टिवेशन एनर्जी का इफेक्ट देखेंगे. अगर एक्टिवेशन एनर्जी लो रहा तो क्या करने का, एक्टिवेशन एनर्जी हाई रहा तो क्या होगा. So that will have an effect in this case. Okay. So product distribution can also be controlled by K1 by K2 by changing temperature. If activation energy are different, then K1 by K2 can be changed. If they are similar, then कुछ effect नहीं होगा. Right. So in this case, okay. So K1 by K2 is nothing but this K01 by K02, some constant, e raised to power minus E1 minus E2 by RT. Now if E1 is greater than E2, so that means activation energy of reaction 1 is more than that of reaction 2. K1 increases more than K2. ये हमने कैलकुलेशन करके देखा था E1 10,000 और E2 8,000 लेके, तो 400 पे 0.57 था, 600 0.67 था वगैरह कुछ आया था, K1 by K2. So K1 by K2 increases as temperature increases when E1 is greater than E2. The reaction should be done at highest possible temperature to maximize R when E1 is greater than E2. Any questions on this temperature effect? बाद में separately देखेंगे, I think unit 6-5 में आता है वो temperature effect. But here I have introduced conceptually what is the effect of temperature on product distribution. And the other case is when E1 is less than E2, that means K2 increases more than K1, and in this case we had seen क्या होता है, temperature reduce किया तो K1 by K2 increase होता है. So in this case the reaction should be done at low temperature or lowest temperature possible to maximize R. Any questions on what we have seen so far? It's a revision only, but brushing up is important, otherwise you will not be able to carry forward. If there is no question, then let us see. The other option is by using selective catalyst, which will accelerate desirable product and depress the undesired product. This is the most effective way of controlling product distribution than any other method. And that's why you will see many processes which you must have seen in CPT. Many of them are catalytic processes, heterogeneous, mostly heterogeneous. Okay. So summary of qualitative findings. Concentration reactants is the key to proper control of product distribution. High reactant concentration favors reaction of higher order, A1 greater than A2. Low concentration favors reaction of lower order, A1 less than A2. And reactant concentration has no effect on product distribution of the same order, A1 equal to A2. So this is a summary. And since you are going to have MCQs, ये सब कुछ आ सकता है, right? So you must start looking at it from MCQ perspective also. Understanding definitely है, but MCQ में ये सब आ सकता है, ठीक है? So second case we saw was if there are two reactants. Generally एक reactant नहीं रहता है, polymerization में रहता है एक single reactant, decomposition में रहता है, but most of the time you will see at least two reactants. So if there are two reactants, A plus B, giving R and S, desired and undesired product. So in this case, you can write RR is equal to K1 CA raised to power A1 and CB raised to power A3. I have taken order A1 and A3 for the first reaction, A1 for A and A3 for B, and RS is equal to K2 CA to power of A2, CB to power of A4. So A2 is for A and A4 is for B. So if you divide 1 by 2, what you get is RR upon RS is equal to K1 by K2, CA to power A1 minus A2, CB power A3 minus A4. ये हमने सेम रखा है because ये फर्स्ट हम एनालिसिस ऑलरेडी कर ली है A1 A2 का. So now we need to look at A3 A4 का इफेक्ट क्या होगा. Okay. So if you want to maximize R, factors which are there are K1 K2 temperature effect. K1 A2 A3 are fixed, right? K1 K2 will have only temperature effect, but at any temperature, fixed temperature, K1 K2 is also constant. Now if you look at this equation 3, if A1 minus A2 is positive, then CA should be high, हमने पहले देख लिया था, and if A1 minus A2 is negative, then CA should be low, ये पहले consider कर लिया हमने, right? Similarly, you can look at A3 minus A4. If it is high, then CB should be high, and if A3 minus A4 is negative, then CB should be low, similar to what we have done before. ठीक है? Any questions? So two or more reactants case, combinations of high or low, that CACB reactant concentration can be obtained by controlling concentration of feed, having components in excess, or by using correct contacting pattern, that is reacting fluids, MFR, PFR combination. And then we had seen some cases, right? So if I want, these are different contacting patterns which are shown, various combinations of low and high concentration of reactants. And this is for non-continuous reactor operations. So if you want both CA and CB high, that means A1 is greater than A2 and A3 is greater than A4. That means we need to have CA high for this case and CB high for this. So in this case, what you take a batch reactor, add A and B all at the same time. So जितना भी रहेगा ये CA naught रहेगा, ये CB naught रहेगा. You add it. Initially it will be high concentration, right? And then धीरे धीरे कम होती जाएगा. Right? So if you want, if A1 is less than A2, that means we need to have low CA, and if A3 is less than A4, we need to have low B. So both have to be low. In this case, we add A and B slowly. So this is CA naught, CB naught. जितना ऐड करेंगे यहाँ पर वो रिएक्ट हो जाएगा, right? So concentration will not build up in the reactor. ठीक है? And in this case, if CA has to be high, that means A1 is greater than A2 and CB low, that means A3 is less than A4, then we need CA high and CB, CA low and CB high. उल्टा हो गया ना? अरे पॉइंट आउट करो ना मिस्टेक. Right? So if A1 less greater than A2, then we need CA high, and if A3 less than A4, then we need CB low. So in this case, what we do is take A in the reactor. Oh, sorry. This is CB naught. Oh, start with A. Sorry. उल्टा कर दिया मैंने. Okay, अगर उल्टा रहा तो that's what I was explaining. Okay. This is CA naught, and then we add CB. तो क्या हो जाएगा? A तो रहेगा, CA तो रहेगा high, but CB जितना भी आएगा रिएक्ट होते जाएगा. That means CB will be always low and CA will be high. अगर उल्टा रहा, if A1 is less than A2 and A3 is greater than A4, तो उल्टा करना पड़ेगा. यहाँ पर CB लेना पड़ेगा, यहाँ CA लेना पड़ेगा. This same batch बस continuously ऐड कर रहे हैं यहाँ पर these two reactors and this batch reactor. Any questions on this contacting pattern? ठीक है. There are no questions. Let's go to continuous operation. क्या करेंगे? So if you want CA and CB both high, A1 greater than A2 and A3 greater than A4, then we look at plug flow reactor. Plug flow reactor always gives high concentration. So दोनों A और B feed किया यहाँ पर. So we'll always have high concentration throughout the reactor for A and B both. Or you can have n number of MFRs or large number of MFRs, and we have seen that when the number of mixed flow reactors increases tends to infinity, then it is actually showing the performance of a plug flow reactor, right? So in this case we add CA naught CB naught, यहाँ पर जो रहेगा फिर दूसरा रिएक्टर थर्ड रिएक्टर से सीरीज में लेने का. So it gives equivalent to PFR performance. If A1 is less than A2 and A3 is less than A4, that means both are low, then what we do is we take a CSTR and continuously add CA naught and CB naught, because immediately ये CA हो जाएगा और ये CB हो जाएगा, immediately कम हो जाएगा. And if you want one high and one low, that means CA high CB low for this case, then you take a plug flow reactor और A डाला हमने, ये हाई चाहिए तो plug flow A will be in PFR mode and B को हम continuously add करते जाएंगे. So this will be PFR. Or we can have another option similar to this one. You have n number of MFRs. So you add A in the beginning for the first reactor, it will go to second, third, fourth. So this will be like PFR mode, and B को each reactor में separately वो add कर दिया जाएगा. So it will be like mixed flow reactor. These are various options for obtaining low-high combination of A and B. Any questions? समझ में आ गया सबको? याद आ गया सबको? ठीक है. There are no questions. Let's proceed to next one. Quantitative discussion. So that was qualitatively क्या कर सकते हैं? But ultimately we want to calculate conversion and yield, right? कितना बनता है? So that is quantitatively how do we handle it? So in this case, we are taken as reaction A goes to R. So we define a term called psi, which is called instantaneous fractional yield of R. That means moles of R formed divided by moles of A reacted at any point in time. Right? Anywhere in the reactor, कहीं भी रहेगा, इधर बोलो. Anywhere. So at any point in the reactor or any place in the reactor, what is the ratio of R formed to A reacted, right? And that is equal to DCR by minus DCA, because we defined DCR is CR minus CR0, that means final minus initial concentration, and DCA is final minus initial concentration.
सर
Yeah.
सर वो साई तो 1 हो जाएगा ना फिर, क्योंकि एक यूज आ रहा है ना, जितना आर फॉर्म होगा उतना ही रिएक्ट होगा.
Good question. How do you handle it, Javendra?
सर वो साइड रिएक्शंस भी कंसिडर होंगे क्या?
Of course होंगे. Just we are defining it, right? Yeah, point ये है कि what is saying is DCR equal DCA होगा क्या?
सर मेंशन कर सकते हैं ना, एक यूज आर एज पैरेलली, एक यूज एस, अगर मेंशन किया तो.
सर दोनों का रेट कांस्टेंट अलग होना.
Yeah, we are talking about only one reaction here, right? And defining this, we are defining the terms, right? We are just defining instantaneous fractional yield क्या है? Just a term definition है ये. Okay. Now we have never said, first of all, the reaction है या बराबर है. When you say A goes to R, 1 mole of A equals 1 mole of R, right? तो जितना R form होगा उतना ये react होगा. But that is not always the case. यहाँ पर ठीक है, A goes to R ही दिया है, but that's not always the case. Not in all the reactions. General reaction दिया है. Suppose ऐसे A goes to NR. Doesn't matter, right? Reaction क्या doesn't matter. Does it matter to calculate this and this? Whatever.
सर अभी आया समझ, एन लिखा तो समझ में.
See, general, see, ऐसे general दिया कि एक reaction consider किया है. You consider any reaction, doesn't really matter. And most of the time you'll not see A goes to R. General लिखते हैं, but ठीक है, because it's simple to write. You always start from simple things and to understand it. But it can be any reaction. A goes to 2R, A goes to 0.5R, it goes to anything. And generally, क्या होता है? See, this type of reaction is there in polymerization. Polymerization, there is n times A goes to R रहता है, right? Because n molecules of monomer give one polymer molecule. So it is never A goes to R. A goes to R is very very rare. But yeah, generally जैसा भी है CRE में A goes to R ही लिखते हैं. But doesn't really matter. What we are looking at is कि कितना R form हुआ, कितना A react हो गया. Yeah, in this case, yeah, if it is A goes to R really, then yeah, it will be 1. In that special case, yes, definitely it will be 1. which you are saying above, but not always. ठीक है? Okay. So for any reactor, DCA is essentially we are defining it CA final minus CA naught. So fraction of A reacting at any instant which is converted into desired product. ये PSI क्यों लिखा था मेरे को पता नहीं.
सर
साई हो गए साई ये साई.
सर
हाँ.
पॉलीमराइजेशन में हमेशा साई की वैल्यू लेस देन 1 होगी.
लेस देन 1 ही होगी. यस. Yeah, but polymers generally side reaction नहीं रहते. See, this is we are considering only when there are two competing reactions. Okay, when there's an undesired product. Polymerase generally एक ही desired product करता है, undesired product नहीं रहता है. There are many reactions which there is no undesired product, but yeah, there are many which have undesired product also. So we have to handle both situations. Okay. So this psi, this is what actually how we pronounce it, psi. This term. So psi is a function of Ca. That means ये जो देखा हमने. Since A changes throughout the reactor, psi will also change with position in the reactor. This is especially TFR. MFR में इतना नहीं होगा, but MFR में हो सकता है because it's not perfect, right? Perfect mixing कभी नहीं होता है MFR में भी. So concentration can be different at different places. Average we say it is okay because this is Ca naught and this is Ca. We assume it's a average concentration of exit. But in the reactor, it can be different value here, different value here, different value here, different value here. Because mixing is not perfect. ठीक है? So, any questions on psi? Okay, so next is phi, which is overall fractional yield of R. So, total कितना बना? Instantaneously in the reactor कितना बन रहा है कहाँ पर is okay, but not as important as how much is actually formed at the exit of the reactor. Because ultimately we are not going to see कि अंदर क्या हो रहा है. We are mostly tracking input and output, right? So then we define phi, which is overall fractional yield of R, which is called phi. So fraction of all R treated, all A treated, that is converted to R. जितना भी A आया यहाँ पर, उसका कितना R बना. Right? Similarly here, how much of CA is converted to R. So it is the mean of all the instantaneous fractional yields inside the reactor. जितने fractional yield रहेगा, instantaneous fractional yield, उसका mean है और average है at all points within the reactor. So phi is all R formed. That means total R formed divided by total A reacted. So total R formed is CRF because we are assuming कि CR0 is 0. If 0 नहीं रहा तो हमारे CR0 रहेगा divided by CA0 minus CF. You can write this phi as CRF upon minus delta CA because delta CA is nothing but CF minus CA naught. Okay, so we can say that this is nothing but psi bar in the reactor. That means mean of all the instantaneous fractional yields in the reactor. You understand the difference between instantaneous and overall fractional yield? Okay. Okay, if you have no questions, let's proceed. So overall fractional yield represents product distribution at the reactor outlet. Proper averaging of psi depends on type of flow in the reactor. TFR रहा तो क्या होगा और MFR रहा तो क्या होगा because instantaneous fractional yield is different in both the reactors. So psi we are saying DCR upon minus DCA and phi p we are saying this is equation 4. So we integrate 7 क्यों बोला मैंने 7 ऊपर था क्या 3 आना चाहिए ठीक है. So if you integrate 3 DCR, ये इधर वाला term is equal to minus psi into DCA, integral from CA naught to CF and here CR naught to CRF. So what you'll get is CRF minus CR naught equal to minus integral CA naught to CF psi DCA. And this is nothing but equal to CRF is CA naught is equal to 0. So if we substitute 5 in 4, what it is 5P, we are looking at plug flow reactor minus, ये minus है यहाँ पर, right? Because we have to looking at the substituting, essentially we are substituting for psi r, CRF. CRF के लिए यहाँ substitute किया हमने. What you get is minus delta CA. Delta CA is nothing but, what is delta CA? Minus delta CA is equal to
सर CF minus CA naught.
ठीक है.
Yes.
That's why it's minus here because नीचे का term same आना चाहिए ना, CA naught minus CF. That's why I kept it like this. Minus of 1 upon CA naught minus CF integral psi DCA CA naught to CF. ठीक है. Equation 6. Okay. Or you can write it as, there is nothing but ये minus है तो ये minus minus करके plus हो जाएगा 1 upon delta CA integral CA naught to CF psi DCA. It is equal to 5P, that's for plug flow reactor. Or you can write 5P into delta CA is equal to integral CA naught to CF psi into DCA. So different ways of writing the same equation for a plug flow reactor. So in this way, psi, that is instantaneous fractional yield for a plug flow reactor, is related with phi, which is the overall fractional yield of plug flow reactor. ठीक है. So next is MFR. The concentration in MFR is CF throughout, assuming it is ideal MFR. So जो भी रहेगा यहाँ पर assuming it is same C है. So psi is the same throughout the reactor and hence phi or overall fractional yield for mixed flow reactor is supposed to be equal to psi, which is the instantaneous fractional yield for mixed flow reactor, assuming it is constant throughout the reactor. Okay. ठीक है. ये एक्सप्लेन किया था मैं इंटीग्रल और नॉन इंटीग्रल क्यों नहीं आता है PFR के लिए. ठीक है. So firing reactor phi is equal to all R formed upon all A reactors CRF upon CA naught minus CF and CRF is equal to phi into CA naught minus CF. ये वाला इक्वेशन is equal to 5P for 5P into delta CA for PFR and is equal to psi into delta CA for mixed flow reactor. So PFR में हमारे को ये कैलकुलेट करना पड़ेगा and MFR में ये चाहिए. And we are going to solve many problems where we try to find out the values of 5P and psi. ठीक है. Any questions on what we discussed so far? ठीक है. If there are no questions, yeah, this is shared and dashed area to be total R form. So R form इससे जो है इंटीग्रल जो रहेगा वो देखा है ये प्लॉटिंग psi वर्सेस CA. प्लग फ्लो रिएक्टर रहेगा तो एसेंशियली क्या रहता है CA नॉट इज हाई तो psi हाई ज़्यादा रहेगा और CF is low, so it will be like this, something like this, not exactly same, right? So in this case, because we are talking about integral, right, 5P is nothing but integral CA naught to CF psi DCA 1 upon delta C, right? So यहाँ पर जो रहेगा ये डेल्टा सी है, राइट, और डी सी है, और ये y है. So y integral will be nothing but area under the curve for plug flow reactor. ठीक है. Just like we saw for performance equation, plug flow reactor के लिए always area under the curve रहता है. Mixed flow reactor के लिए ये psi है, right? Psi into delta C, right? Psi into delta C है. This psi, which is the value, suppose this is the exit concentration CF है, right? ये concentration पर जो psi value है, this into delta C. That is a CRF value for mixed flow reactor. That's why you will see that there's more for plug flow reactor here CRF and less for mixed flow reactor. So हमें difference mixed flow reactor plug flow reactor का area under the curve or rectangle area. This we had seen before also, but same concept is coming here also. Whenever this plug flow reactor, we always take area under the curve. Whenever there is a mixed flow reactor, we always take the area of the rectangle for that particular value. And if it is stage reactors or n number of amphors in series, so depending on the value of CA, suppose this is the first reactor, CA naught यहाँ पर है, CA naught है, और ये CA1 है. तो यहाँ पर जो psi रहेगा उसके एरिया अंडर द कर्व लेंगे, रेक्टेंगुलर एरिया लेंगे. सेकंड रिएक्टर में CA1 इनलेट रहेगा, CA2 आउटलेट रहेगा. So again this is the value of psi, this is psi1, this is psi2. So this is psi2 into delta CA, CA2 minus CA1, CA1 minus CA2, and this is psi3. So psi3 into CA2 minus CF. So this is the third. तो ये रहेगा CR. ठीक है. Any questions on graphical interpretation for finding R? ठीक है. So now if you look at contact with the largest area produces most R, plug flow is best, right? So we see A is a plug flow, right? जो ऊपर देखा था वैसे ही है. तो इसमें देखा हमने एरिया अंडर द कर्व इज फॉर PR प्लग फ्लो रिएक्टर, दिस फॉर प्लग फ्लो रिएक्टर. एंड दिस फॉर मिक्स फ्लो रिएक्टर. मिक्स फ्लो रिएक्टर में जो फाइनल कॉन्सेंट्रेशन रहेगा ये psi रहेगा वैल्यू, राइट? तो यह इस पे रेक्टेंगल का एरिया रहेगा. प्लग फ्लो के लिए पूरा ये रहेगा. If you take mixed flow, in this case, if you get this type of curve psi versus CA naught, because here the value of this CAF, so this is the value of psi. So in this case, you get maximum R for mixed flow reactor. That means essentially we need low CA, right? यहाँ पर high CA चाहिए, यहाँ पर low CA चाहिए, जो हमने देखा था, right? This is the value of low CA. Low CA में यहाँ पर mixed flow reactor में maximum R मिल रहा है. यहाँ पर high CA तो plug flow reactor में ज़्यादा मिल रहा है, right? And if it is a combination, mixed flow up to A1 and plug flow is the plug flow after that. So mixed flow रहेगा तो ये psi value रहेगा. So this is the area of rectangle. और plug flow रहेगा तो you take area under the curve. So depending on whether it is mixed flow, plug flow or combination mixed flow, plug flow, you can fit the area and R formed. Any questions on these diagrams? Yeah.
सर वो कर CF से बाहर क्यों जा रहा है सर? क्योंकि फाइनल तो CF है.
क्या बोल रहे हैं?
सर जो कर दिखा है ना 7.4 ABC में, तो वो CF से बाहर जा रहा है ना वो कर, आगे जा रहा है.
ऊपर कट कर देना चाहिए, right?
यस सर.
Okay, don't nitpicky मत करो. It's a curve, smooth cut rod. Suppose I change the value of CA naught. No, curve ऐसे रहेगा. Suppose I change the value of CA naught. And this is the value of CA naught. And this is the value of CA. तो कर्व ड्रॉ किया उसने. That's okay. We are just saying कि ये कर्व रहेगा, ये type of curve है. And now we are fixing what is CA naught. CA naught value can be here also, right? I can change the value of CA naught. Instead of this, I can take this value of CA naught. I can change the concentration. No? Ultimately, I want to say कि कौन सा concentration, कौन सा combination will give me maximum R, right? क्या करना चाहिए? So this is basically for studying all those things, options.
Yes.
Combination रहेगा या plug flow रहेगा या mixed flow रहेगा तो कैसे करने का, कैसे evaluate करने का, graphically कैसे कर सकते हैं. We'll not do graphical calculations, numericals, but we'll do mostly numerical or calculation will be using these equations, not graphs. But ये बताया कि graphically कैसे कर सकते हैं. If you have graph data, if you have the curves. Any other questions? Okay, so that was the revision of what we had done so far in Unit 4. Next time we'll solve some numericals based on this quantitative discussion or quantitative equations which are different IP and psi. And we'll calculate what is the maximum value of R which is formed in different configurations of reactors.